All right. So now let's get to the fun part, where we're gonna define a triangle in memory. And this is a little bit different, I think, in WebGL than what you probably have done before. But I'm gonna define a variable here and say this is a triangle. And a triangle for me is gonna be an array, okay? And this is gonna be an array of 6 elements. And why 6 elements? I wanna define the XY position of the 3 vertices of the triangle. So a triangle has 3 vertices, and I want to define those, but using one array, okay? So what I wanna do is I wanna say minus 0.5 minus 0.5, and this is the X and Y coordinate of my bottom left vertex. And I'm gonna define now a second vertex saying 0.5 minus 0.5, okay? And I wanna define the X and Y of my final vertex, which is 0.0, 0.5, okay? So here we are, I'm gonna comment this, we are create a triangle, or define, let's say define 3 vertices of a triangle as a list, or as an array, sorry. So that's it. And when we see this, I'm going to discuss why I'm putting these numbers here. For now, you don't have to worry much about why this 0.5 or minus 0.5. But when we see this triangle on the screen, then we can play with these numbers, and I'll explain why I actually want these numbers for now. But this is just arbitrary numbers for now. Any three sets of points would make a triangle, right? In 3 different points. But I'm picking this just because they were going to look nice when we visualize them. Let me print this. Okay. So there you go. We have this list there. It's working. Nothing really special here. We have seen arrays in the last assignment. But now, I think this is when it starts to get a bit complicated. So I think this is a very important concept that is very different when you're doing graphics, which is the idea of shaders. You probably have heard this word before, or have even programmed a shader. I don't know. Most of you probably didn't. So basically, a shader is a program that lives in the GPU. So most of you, as programmers in our CS majors, most of you have done only programming in the CPU, or since our virtual machine, if you have done Java, you use the virtual machine and you ran your code in your virtual machine. Python has an interpreter, but if you wrote C code, you ran code for the CPU, and all of these examples that I gave at the very end, they actually boil down to a CPU execution, even though some of them have virtual machines. Now we're going to start writing code that literally runs on the GPU. And because of that, we will see that this code is fairly different from normal C code or JavaScript. So we are entering now the world of shaders, and we want to learn a new language, or a new programming language that looks a lot like C as well, but this is called JLSL, which is like the language for writing GLSL, which stands for WebGL Shading Language. And this is, we're gonna start writing simple shaders in this assignment. And this is one of the key concepts of this lab. So, as I mentioned, shaders are programs, right? So we normally write programs as text, right? We have a text editor and you type, like for example, JavaScript code, which is compiled or interpreted. And in GLSL, we're gonna be similar, but we're gonna actually include our shader programs as part of this text file here. So this is gonna be a fun and different experience. I'm gonna define a variable here called Vertex Shader. And this is a string, okay? Because again, a program is at the end, it's a huge string that gets compiled. And in this case, we're gonna write a program in here. And this is gonna be one program. I also am gonna have something called the Fragment Shader. We're gonna have two shaders. And this is also a string. Now right now they're empty. So, but this is one program and this is gonna be another program in string formats. And we're gonna use GLSL programming language to write this code, to write the shaders. Let's just say GLSL to write this shader, these shaders. So basically in graphics, we have two major types of shaders. If you look it up online or look in the literature, other platforms and other framework, graphics frameworks, they might define other types of shaders, but honestly, like in the Webgl pipeline, we have only two shaders, and it's very useful to, even if you're working with, let's say, DirectX or other graphics frameworks, it's useful to think, or all of them kind of boil down to these ideas of vertex and fragment shader. But so basically, these are going to be two independent programs that will be shipped to the GPU, at first compiled and then shipped to the GPU. And they're going to do some operations for us. And we as programmers can define what of these operations they're going to do. So let me start by writing a very simple vertex shader. And what is the goal of the vertex shader? And let me explain the difference between vertex and fragment shader. So the vertex shader takes as input a bunch of vertices, or in this example, it's going to take as input this triangle here. And it's going to manipulate this triangle or in certain ways. And this is arbitrary ways that we can define as programs. It turns out there is some common operations that we normally do in every application, and I'm going to discuss them later. But the vertex shader is pretty much a program that manipulates vertices. And then it outputs also a set of vertices at the end. So normally what we want to do with these vertices is some sort of transformations. We want to transform these vertices in certain ways. And this is going to depend a lot on the application you're writing, or on the, we're going to want to do some transformations. And if you want to do some transformations, we're going to do this in the vertex shader. This gets passed through the fragment shader. So the output of the vertex shader is going to go and become an input for the fragment shader. There is some processing before. You probably have seen in the class the Webgl Pipeline, and if you haven't seen yet, you're going to see for sure. And the Webgl Pipeline has this this organization where you have the vertex shader first, and then you have something called rasterization, which takes these vertices and transform them in a set of fragments or kind of pixels. So the fragment shader, instead of operating on vertices, it operates on pixels. So then the job of the programmer when writing a fragment shader is deciding how to color or how to shade these pixels. So quick important information, the input of fragment shaders are pixels, or also called fragments. And the input of the vertex shader is pixels, and this is the input here is vertices. Okay. So let's play with this. So shaders are fairly complex thing to understand, and you have to work with them a lot because the way you program them is they're very different. Something that is interesting about shaders is that they run in parallel. So we will see what that means when you start writing things. But let me start with the first line of the vertex shader, and this is normally defining the precision of our types. So here, don't worry much about this line, but what I'm doing here is I'm setting the precision of a float to be a medium P. And a GLSL is very similar to C. It's a typed language, so you're gonna have to define types for your variables. And you have a main function similar to C, and I'm gonna write it here, void main. And this is our main function of our vertex shader. Void means that it doesn't return anything. So the functions also have to, you have to define the returning types of the functions. So basically, this is the major structure. And here we're gonna write some operations inside the main function. Similarly, also the fragment shader has a main function. And here we're gonna have to define the precision as well. Precision, medium P. This is also not very important, but it's required, so I'm typing this here. So what I wanna do with this vertex shader is just what we call a kind of a pass-through shader. I don't wanna do anything on this vertex shader. I don't wanna do any operation. I wanna get my triangle and just literally, I don't want to do any transformations by now. We're going to see in the next assignment that we're going to, for example, if you want to rotate or scale or a certain shape, we're going to need to do transformations in the vertex shader. But now we just want to draw the triangle as it is. But even for that, we're going to need to write at least one line. And this is an important introduction here. We have to do this. So in GLSL, we don't use the return statement. In GLSL, our return is pretty much setting this variable GL_position. And you have to match exactly this name with the capital P here and all of that. What you're doing here, you're changing a very special variable in your, you can think of this changing in the GPU, a special variable that is the position of your vertex. But what is interesting here is that I have here 3 vertices defined as an array. So this shader here is gonna execute in parallel or at the same time for these 2 guys, these 2 guys, and these 2 guys. So exactly at the same time, at once. So I don't have an array here. I just say GL position equals 2 because this is going to run for every vertex in parallel. And what this is going to do is I'm just saying, I'm going to write this vector 4. Let's make a variable first. Actually, let me make a variable first. I'm going to call this an attribute vector 3 a position. Or sorry, let's do this vector 2 first. So here, what I'm saying is I'm creating a variable with name a position. And this a underscore here is a prefix that I use because this variable is of the type attribute, or the type is actually vector 2. But in Webgl, you also have this second type, let's call, which we have only 3. We have attributes, we have varyings, and you have, I forgot, is the global variables. I forgot now the name. Sorry, just blanking. But you have 3 different types. Uniform, sorry, I forgot. So it's a uniform attribute, and varying. So we have three types. We're going to use attributes here. And then this is our type vector. So in GLSL, we have vectors already built in. We have vector 2, we have vector 3, we have vector 4, we have matrices, we have many types of like kind of already complex data types defined for us. And this is going to be a vector 2, which is pretty much a vector which has coordinate x and y. What I want to say here is I want to cast this to be a vector 4. And I want to say this is a position 1, 0, 1, 0. So there is a lot in these 4 lines of code here. 1, 2, 3, 4, 5 actually. So here I'm defining the precision. Here I'm declaring this vector 2 of type type attribute a position. Then I have a main function, and here is my kind of return statement. It's kind of like our return statement. And what it does is this vector 4 open close parenthesis is a casting operation. So I'm transforming this a position from being a vector 2 to be a vector 4. And why is that? Is because GL position has to be a vector 4. So GL position is expected to be, and if you don't return a vector 4 here, you get a compilation error, and it is not going to work. So, but I'm calling this vector 2 because each of our vertices, they have only x and y coordinates. If this was a 3D shape, we would need a z coordinate, right? So you would need a third dimension here, and then here you would have a vector 3 to represent position. But now we are working on 2D, so let me keep this simple with vector 2. But regardless of this, we're going to have to make this vector 4. And it's funny because it's very cool how you can do this in GLSL, because look at this notation. I'm putting the variable here as the first argument, and then I'm having 2 arguments here, 1, 1, which is pretty much thinking. So what this does is it's going to return the following vector. So it's going to take the first two x and y coordinates of a position, and then it's going to concatenate 1 as a z and 1 as a w coordinate. So pretty much this operation here is concatenating these two numbers to this vector. And let me make this 0, because by doing this, I'm setting the coordinate z to be 0. And I want to keep for now the last one to be 1, because we're going to talk about this 4th dimension later in graphics. This is used for specific things, and let's just keep it as 1 now. So, but yeah, again, this is when things start to get maybe counterintuitive. So let's stop and let me check for questions. Do you guys have any questions? Let me check the chat. Okay, so I got a question saying, why put 1 and 1 in the vector 4 instead of 0 and 0 if it's 2D? So yeah, I changed the z to 0. Basically, yeah, that makes more sense, because we're kind of like we don't want that, or we don't want the z dimension here. But the w coordinate, we're going to keep it 1, and this is going to be, it's not going to change much for now, I think. But when you start doing transformations, this is going to matter a lot. So let's keep it for 1, and this should be the default number for the 4th dimension. Okay, so, but overall, you're going to practice shaders a lot in this course, and this might be a kind of like counterintuitive or kind of weird in the beginning, but you're going to get familiar with this. And this is one of the coolest part of this class, I think, is like learning how to do shaders. Because basically this is your interface to the GPU. If you want to do any programming on the GPU, you're going to write shaders in one form or the other. And then just a side comment on this is that if you're doing nowadays machine learning, which is like AI applications, now all of them use the GPU for computation, either for training or for running, for example, neural networks. And if you want to, when you use, let's say, frameworks for AI like TensorFlow or PyTorch, they actually use shaders under the hood to do these computations. And it's really nice to learn actual GPU programming. And because I think moving forward, in our careers, this is going to be even more useful, more and more than it used to be, I think, for general purposes or for other applications than graphics. Okay, so, but this is it for our Vertex Shader. Overall, what this does, it literally does nothing. It just like takes the position and just sets the GL position to be that position. It turns out we have to do a casting operation here, but literally what you're doing is just sending the attribute as it is. And speaking of that, what is an attribute? An attribute, as I mentioned before, we have three types here. We have attribute, we have uniform, and you have varying. We're gonna use these three types a lot. So basically, we could have like these three combinations for example, positions. And the attribute in this case is a variable that is different for every vertex. So this means that a position is going to be mapped in the shader for this, and for this. So we're going to have kind of three parallel executions with three different values for a position. If you want to instead have one unique value, you can use uniform, which is this variable that is shared among vertices or across the shader executions. So this is a uniform variable. Variable is similar to global variables in regular programming languages. We're going to use this actually for changing color in this lab, but let me just introduce it now, and later we can discuss them. And a varying variable is this variable that you use to as an interface between the Vertex Shader and the Fragment Shader. So basically, if you want to pass any variable from the Vertex Shader to the Fragment Shader, you can define a varying. And varying variables, they have to coexist in the Vertex Shader and in the Fragment Shader. So for example, if I had a color, I'm making up an example here, that if I had a varying color here, or let's say a vector 3 color for RGB, I would have to have the same line of code here in the Fragment Shader. Because the GPU would automatically send, not automatically, but here I could use and set this variable, for example, to be something. Let's say I could say vector 3. If I want to make it red, I could do this. And now with this line, because I'm typing this, when I run the Fragment Shader, this variable is going to have 100 in it. So basically, the varying variable is this interface between shaders. We're not going to use it in this assignment, but we're going to use it later. So let me go back and have just the position in the shader. And that's it. And now I want to talk about the Fragment Shader. So any other questions about the Vertex Shader? And it's fine if it's a little bit confusing now. The book has tons of examples, and it goes very slowly on all these lines, and there's like references for varyings and attributes and all of that, and discusses all this all these little details of GLSL. So it's like the book is very clear and very helpful on this on GLSL.